We have come a long way with new approaches and new ways of thinking. And what we've been hearing this morning is different approaches, different ways of looking at security. And one of the things that has been a problem forever is the management would say, looking for a management porn excuse or pretty picture, they say, are we secure? Can we answer that question? And we really cannot answer that question ever by saying, yes, it does not exist. Security as a perfect answer doesn't exist. So I wanted to look at, and some work I've been doing for many years now, is looking at how to design security systems with measurement in mind. I've been using a lot of these ideas and axioms as to how to think about security, whether security is at network level, whether security is at the physical level, whether security is at the human level, because we have to make these all work together. And so over many years of looking at the world through an analog lens instead of a digital lens, I've come up with a lot of different ideas. We know what we're doing isn't working. We know that the fundamental model that we are using for most network security is based upon the work of Anderson from 1972. And one of the premises that I use is that digital is not binary. We want to think, and our managers want us to think, either or. Either we are secure or we're not secure. And I have ended up over the years thinking much more like an ICS person, industrial control system, because they have it a lot more right than we do. And we are stuck. One of the problems that we have is the concept of infinity. If we expect security to ever be perfect, we are going to have to reach infinity, which is obviously going to be impossible to do. And when we look at ICS systems and other analog control systems, there is no infinity. There are limits. And Joe was talking a moment ago about min and max, minimum and maximum conditions. And when we look at security, if we start thinking that way, we're going to end up with some different answers. And this remote is brilliant. So I'm thinking, if you're clicking for me, thank you. What we need to do is get rid of zeros and ones when we think of ICS systems, and I'll get into some of that in a little more detail. There are no zeros, there are no ones. There are continuously variable functions that are measurable. And one of the biggest things that they use that we do not use very often is the concept of feedback in the systems. Every engineering project in the world, with the exception of computer science and IT security, uses feedback in order to control the process, in order to keep it for the system from trying to reach infinity or ever being able to reach zero or completely non-functional. And part of the concept that we're going to have to deal with is the concept of negative time. Everybody wants things to go faster. All the processes have to go faster, faster, faster. And we know that the faster things go, the more room there is for error, because there's not enough time left to be able to make corrections or adaptations unless your feedback system is based upon a loop. And we'll get into the loops. Time ends up being the single metric that works with risk, works with privacy, works with data exfiltration, can work with cost analysis and ROI based upon rates of data exfiltration. Time is the single metric that we rarely ever see in any of the formulas and the approaches we take to security. So that's not too bad the way that did that. The concept began, believe it or not, in a bar in Warsaw in 1996, and it was based upon some work done by DISA, part of the United States Department of Defense. And the concept is very, very simple. How strong is your security protective device? How strong is it? With a number. Will a vendor guarantee performance of that particular protective device? We guarantee our firewall, nobody will ever be able to break into it for 7 days. Does any vendor say that? Or is it 1 millisecond? Or is it 3 years? We tend not to think in terms of time. But now let's go to the physical world. If I am a bad guy and I'm going to break into a jewelry store, well, I got to break in somehow. So let's say I'm going to throw a rock through the window. And we'll also say that this jewelry store is very security conscious, so they have a detection system. Their detection system now knows the window is broken. How long did it take that detection system in the window to know that it was broken by my rock? A guess, how long? A minute? Oh, you got a shitty jewelry store. It should be a few milliseconds. If there's a wire tape around it, it should know instantly, well, not instantly, but very, very quickly, something is broken through the window. And I'm the bad guy, and I know that that is very, very fast. What happens next in the case of a physical robbery? The detection system should call the police, right? Call the armed guards. Call somebody for a response. Now, the bad guys that are smart know how far the police station is away, how long it takes to dial the phone or connect to them, how long it takes the police to respond. They know this. They know this in our cyber attack world today. So when I add up two numbers, detection time, the rock going through the window, and the response time of how long it takes the police, somebody to come back, I end up with a number called exposure time, ET. So what do the bad guys do? They have a watch and they say, we have 3 minutes to steal as much as we can before we have to get out, because that's when the cops come. And in all the movies we see, there's always somebody counting down. We have 2 minutes left. We have 1 minute left. 10 seconds left. Let's get out of here. The bad guys are still doing this not only in the physical world, but they're also doing it in the network world. So therefore, how do I defend? Well, my vendor should be able to say, we guarantee that our protective device will be greater in the amount of time it offers protection than the amount of time of detection and reaction. Pretty straight ahead, pretty simple, the concept. But it's very different than the way management thinks and most IT professionals and security professionals think, because it's no longer dealing with zeros and ones. And when we start looking at network exfiltration, bandwidth suddenly becomes another time component to be able to measure how much, in this case, data exfiltration can occur over what period of time. How many of you have any of this data for your existing networks? I'm going to show you the schematics on how to figure it out. I was talking earlier, feedback systems, the upper right, electrical systems. If there is no feedback, what happens? The microphone squeals. If I have no feedback, the amplifier tries to reach infinity. That mechanical device there keeps trains, steam engines, from going too fast. So there is a limit function. And that's where the expression balls to the walls comes from, is when the balls on that device, called a governor, hit the wall of the casing, that has created the maximum speed condition in that particular environment. All engineering has this. Now in SCADA systems, and I'm going to go back to that, and good ICS systems, time is an integral component of how to calculate a system's performance. So, one of the great examples is in the Netherlands with a thing called the Delta Works. After the 1953 floods, they decided we are going to protect the entire country with a system of dikes and water controls. And how do they do it? They do it with lots and lots of detectors of temperature, of waves, of wind, of heights of water, depths of water, turbulence of the water, the heights of the controls and the physical walls. And none of them ever reach zero. None of them ever reach infinity. They're all within a set of conditions that are designed by the security system of that particular environment. And this is the way that ICS systems do a really, really good job of creating min-max conditions that are permissible within my environment. Instead of saying, I want my processors to go faster, I want faster communication, I want everything faster, and keep security out of my face, which is the approach that unfortunately we've been taking these days. We use this in our daily lives. Has anybody ever used a toilet? Sometimes. Where do you work, sir? A toilet has a ball cock. No water, fills the water, reaches a max condition so the water will not overflow, and it has been picked, when it's working correctly, an optimal condition that is safe. Super simple. Temperature controls, heating, and air conditioning. It never goes to minus 273, and it never goes to, well, we hope it doesn't, unless you're into physics, and it's never going to reach, hopefully, 100C. It'll be somewhere in between. And a detection system, a reaction system, set the minimum and maximum conditions that are permissible for that environment. And then, of course, self-driving cars, same sort of condition. In theory, we're not there yet, and I don't know if we're going to be there for quite a while, are supposed to be able, in theory, to be able to detect the minimum, maximum safe operating conditions of a vehicle on the street. That's future, and that's hope. When we look at neural networks do not have a 0 or a 1. They have something, all of their numbers are a little bit greater than 0 or a little bit less than 1, somewhere in between minimum and maximum operating conditions. And that is where you hear the term bias, data bias, processing bias, weighting bias in AI. They're looking at the problem in the correct way. It's a very, very difficult problem to solve about how to adjust bias And the reason is we do not know yet what is a safe operating range. We can guess, but we'll also disagree a lot. And one of the things that's very interesting about the feedback networks in neural networks is when you ask a neural network a question and you get an answer, then you ask the neural network the same question again. You very may well get a different answer because the mere fact that you're asking a question of the neural network has changed the weighting and bias factor of it itself. So again, all of this is not digital. It is an analog function operating between 0 and between 1. Where's our security feedback? Where do we have it? Where do we have the operational controls to be able to detect before a system starts having a runaway condition? We have runaway acoustics, we have runaway electronics, we have runaway mechanical systems. In our world, that's when we say network collision, and what is our answer? What is our answer? Turn it off, turn it back on again. That is the answer that we've come up with in the last 45 years. One of the approaches that I really like was invented by a colonel in the United States Air Force in 1984. And he wanted to know, in an aerial dogfight with fast fighter planes, who is going to win a battle? Who is going to win a battle? What's the answer? Anybody, shout it out. The pilot? I don't know is a really good one because the answer was not obvious until Colonel Boyd's work. He created this loop, OODA. Observe the environment around me. I'm up in an airplane. What does it look like? Orient yourself towards the other objects and things in that combat environment. Make a decision of how you are going to do something in order to survive, because that is your goal as the pilot, is to survive, and then act on it, and then do it all over again. The answer, who survives a dogfight, is who has the fastest OODA loop. Who can do this the fastest? It's a matter of time. Only a matter of time. And again, we are not taking this approach currently with our general information security, IT security, physical security approaches, because we still live with this binary condition in our minds. Don't you love remotes? That is just a more complex way of OODA, because OODA can become very complex depending upon how many sensors, and sensors becomes a key component with this new way of thinking about security. What do? Well, we have OODA also that'll work with, and there's two kinds of feedback. One kind of feedback is negative feedback. Negative feedback helps control and constrict and define the operating parameters of a system. Very simple. Works all around the world. That's why we have water. That's why we have electricity. Every night between 11:50 p.m. and 12:10 a.m., the frequency of the power line here in Europe, 50 cycles, in the United States, 60 cycles. If you measure it, you'll see it changing, because they have to, by law, have one stable frequency average per day. So they have an adjustment period in between this. That's all part of their loop. With education, we have positive feedback. I want to teach you something. And so we create positive feedback loops, and you're going to be hearing from Dr. Carpenter later about what positive feedback, why it is good in some places psychologically, why it is bad in some places psychologically, and in the world I come from, positive feedback will destroy a system. But they both have OODA functions that have to be defined in order to create a safe operating environment. So let's put some pieces together here. Remote banking. So I've got my phone and I want to Venmo, I want to do something. So I initiate a process. More and more in the last several years, some banks are taking advantage of some of this concept. And they say, we're going to send you an out-of-band code to verify two-factor authentication based upon time. You have 5 minutes, you have 10 minutes, you have some defined limit, operating safe parameters based upon the risk that the bank is willing to take as to how long you should take to enter that code. So what happens? You initiate this process, the process stops. There's a clock, and that clock is driven by policy. And it says, here's how long we're going to let Winn wait before he enters in the 6 or 8-digit code. If I do it correctly, the process continues and I can make my banking transaction. If I do it wrong, based upon policy, 2 times, 3 times, I'm locked out and I must start it all over again. So again, there is no 0, there is no 1. Everything is defined as a function of time, and the safe operating limits of the system are defined by policy and how you are evaluating the risk of your operating environment. So here's my wife's car. She has one of those cars that will sort of tell you there's a Porsche coming down your ass back here, or there's don't turn here because there's a bicycle. And these are a little bit intelligent, we'll say. Now, let's say you have one of these cars and you're driving along and you put on, I'm going to shift lane. Do you trust it? How many people trust it and will make that change? You guys are skeptical security people. How many people will click it, wait, and then turn their head and verify it? Because we don't exclusively trust the technology, we want to have a verification, because maybe there's a Porsche coming up at 160 miles an hour on the Autobahn, and it's just a little too far away from the sensors of my car to be able to detect it. So I keep telling my wife, please do not just trust the car. Let's go back to when we were kids and look this way, look that way, and add that double layer of verification, because what is the metric there? Time. Time. How far is that Porsche away from me? We are really good at calculating how to hit a ball or kick a sock. We can do that. Our brain averages this stuff amazingly well, better than technology still. But too many people are starting to rely exclusively, if I want to change lanes, the car says it's safe. And I think that is very, very dangerous to make that assumption without having a time-based feedback loop during which you can make an intelligent decision. And intelligent remotes. And this comes down to the concept of trust. Who thinks there is such a thing as 100% trust? So none of you trust your wives with your life.
That is correct.
That is correct. Are you married, sir? Why does he keep talking? There is no such thing as absolute trust because the conditions, the context of the environment is always changing. So let's say I'm in HR, I'm going to hire somebody, and I have to decide, what do I care about? Is he technically good? Sure. Has he been a criminal? Well, what kind of criminal? Did he smoke some weed? Did he kill people? There's a difference. And part of the process is building a weighted, as in a neural network, a weighted first guess set of minimum and maximum conditions of where I want to establish the amount of trust that I have, in this case, in an individual. The same thing occurs, or should occur, when I have my network, my business, connected to Dr. Carpenter's. Do I trust Dr. Carpenter's network to connect to mine through an API, and do I have trust in it? Well, that's only because it's you, Greg. I may have trust today. Should I have trust tomorrow as well? Should I have trust in a week from now? Is it a single binary decision, or is it something that I should periodically sense, detect, and reevaluate with a feedback loop? We're not doing any of this in any of our security processes. Everything is changing all of the time. How many changes occur to your network on a daily basis? Any answer? Give me an answer. All right, I'll give you an answer. Maybe 1 billion, maybe 1 trillion, maybe more. Because every time a bit moves from one place to another, the condition of your network has changed. Which ones are important? That's for you to decide. Which ones should be more periodically reviewed and evaluated before trusting that API connection you have with another bank in another country? How long should your trust exist? So let's take a look at this from administration. Right now, in a mission-critical position in a typical server environment, control rooms, SOCs, NOCs, wherever, it takes a minimum of 5 human beings to be able to have 24/7 coverage. 5 people, roughly. Now, in entirely too many of them, they're sharing the same password. They're sharing the same identity, because that single identity is enough to be able to do that. We don't want to make things difficult, do we? We don't want to make it hard for the administrators. So what happens if we take another approach? Let's say that my process is now, and maybe you've had some of this in Europe, we used to have it in the US many years ago, that before I can write a check that the bank will cash, I have to have a second signature called the 2-man rule, or I don't trust my wife to write one. 2-man rule. In some places, the 2-man rule is like 2-factor authentication. I want to have another level of verification. But in this case, with administration, especially for mission-critical systems, let's say Alice makes an administrative decision, presses some buttons, and an action is taken. Now, typically, that's just Alice making a decision. No oversight, no feedback, no min-max control. But what if we set a policy that says after Alice makes a decision, Bob has to approve it. Well, if we do it linearly, we have to wait for Bob to come back from lunch. Maybe Bob is on vacation. Again, it's a matter of time between the period when Alice makes a change and Bob has to make a verification and approve it. But what if we set a policy limit and we say before the system will accept the change permanently, Bob has to approve it. But Bob has to approve it within 3 minutes, 5 minutes, 10 minutes, whatever policy says. This could be perhaps Alice and Bob are pieces of code that have to approve each other within some number of clock cycles or milliseconds. The principle is exactly the same. Taking an action that's mission critical and requiring a time-based feedback mechanism to be able to validate it until the next step is taken. And this circuit is called a time-based flip-flop. Flip-flops are ancient electronic equipment from the 1920s that we don't use much anymore because they're binary functions, and I'm talking about an analog world. So we have to create an analog version of that with an appropriate truth table that goes with it, and the truth table, in this case, invokes time. I'm not going to bore you the hell out of this stuff, but let's look at how things talk to each other. Networks. When we talk about trust, we know there's no such thing as 100% trust. But when I start connecting systems together, something very interesting happens. And I have sorry, these slides are in the wrong order. The way to calculate what happens when more than one object and at least 3 objects start to talk to each other, we use the remote. We use Bayesian probability. When we look at systems under a Bayesian probability methodology and some simple mathematics, it's very simple stuff. When we start connecting systems together, the trust goes way down very, very quickly. And in order to maintain high levels of trust, when you've got multiple systems talking to each other, your initial conditions for each one of those individual systems must be very, very high with its own internal weighting system and its own probabilistic weights to be able to determine how the system as a whole is actually going to work. If you want some of the heavy math on this, I'm going to refer to Dr. Carney down here. He will be here for the conference, who will help you get through this. One of the problems that we have is the concept, and this goes back to the 1940s. It's called a rock curve, and it's how accurate is stuff? How accurate is it? When you got bombs and missiles running around, you care a whole lot how accurate things are. So in our world, we want, what we desire is to be 100% true positive. That's our goal. And in the rock curve, that's all the way in the upper left, but it's never going to happen, never going to be achievable. But we've also got false positive, false negatives, and then true negatives. What we're looking for is as much accuracy as we can, and the dotted line in the middle is average, meaning, you might as well throw a pair of dice to get an answer. Sort of where we are right now with a lot of things. And when we look at this world this way, what we start realizing is that what we think is obvious is not so obvious. I love this picture and I love this analogy for detection and depth. This is a GE NX engine on 777s, 87s. These engines don't go bad while you're flying. Why? Because they are the closest approximation to the human brain in systems engineering today. There are 5,000 sensors inside each engine sampling specific pieces of the operation of inside the engine every second. A transatlantic flight, 400 terabytes of data is collected. Why? For the same reason that the human mind and the human brain functions is for survival, to be able to predict the future. That's what we do. In order to survive, we can predict the future for a few milliseconds, a few seconds, depends upon the context. But when I'm sensing metal fatigue, metal temperature, operational stability, flow rates of oxygen versus and I've got hundreds of sensors doing this, what do I care about when I'm in the airplane? I want to be able to predict failure before it occurs. Because we can fly on one engine and land at a nearby airport. But this engine is as close to the human brain as we have in engineering today. So how do I measure some of this stuff? Let's just take a quick look. And these are things that you can do. Anybody wants the PowerPoints? Great. The book's downstairs if you care. We know from a vendor standpoint, the vendor says, I'm going to be 99% accurate. Is that any good? No, that sucks. Because if you have 100,000 or 200 million emails coming in every day, 99% accuracy says 1% of that million. That's 10,000 that are not going to get detected. So how do we verify what the vendor says? Well, we send in good traffic. So we get a baseline of operation. This is an engineering concept. Baseline operation. It's all good. Cool. Now, what should the vendor be able to detect and call bad traffic in this case? Well, let's build that. And I'm going to inject that into the same traffic path. And while I do that, I'm going to start a clock. And that clock's going to start ticking. And I want to know how long it takes that particular detection system to detect the bad traffic. So the output detects traffic, stops the clock, and what do I have? I now know in this particular environment, whatever it is, how long the vendor's product takes to actually do its job. So does an IDS take 1 millisecond? Does it take 30 seconds? Is it hardware dependent? What other conditions and contexts will change the ability of an IDS of some sort to be able to work reliably within a set of min-max conditions? Take the same concept on phishing. Why don't I, before I allow somebody to respond to an email or respond to clicking to a website in order to avoid a beef attack and perhaps, why don't I institute a clock that starts a process that evaluates the probability of that link or that email being hostile? If I'm really good at my job, I should be able to do that in a couple hundred milliseconds because there's services out there that we have now built into our browsers that'll do it. So all I want to do, let's turn off SMTP on that particular communication until I have a probabilistic evaluation of the risk that that particular link has. The numbers are simple. The thinking is simple, but we have not gone this route yet. Now, to finish the argument, detection and reaction to understand how much protection I really have or really need. We do the same thing. Once my detection test is known, I want to know what is my reaction process. Do you have an automatic reaction process as part of a SOAR platform? Okay, that should be pretty quick. Measure it. Have any of you ever measured the response of SOAR to a detection? Why not? Gives you a lot of answers, because then it gives you the vulnerability and risk as a function of time throughout your operating environment, whether it's at code, network level, human or physical interactions. Now, some people say, I'm going to use two. I'm going to use two IDSs. So they go, well, if either one of them picks it up, I'm good. Unfortunately, that's the wrong answer. Because if I use two independent malware detection systems, and if either one is triggered, the reliability actually goes down significantly. And again, this is using Bayesian probability analysis. What I want is both systems to agree within a specific period of time, just like we did with Alice and Bob identifying themselves to a system. The principle is the same, the math is the same, everything about it is identical, except how do you actually implement it, and are you ready to think differently? So what can you do? Go off and measure some of these things. Take a look. Take a look at your systems. Benchmark them in the laboratory. Look at the vendors' products. And this is all stuff you can do. It's not a whole lot of code to do any of this. Mark's going to probably write. You're going to write all the code? No, I'm not going to commit him to writing all this code. What we need to do is start looking at these systems using intrinsic feedback systems, looking at OODA systems, because one level of feedback is one level of attribution feedback for one small piece of time. This has to be a continuous process. Think in terms of network security as a bear. Greg and I are out hunting. We're hunting bear, we got our gun, and all of a sudden there's a bear, and it starts chasing us. Greg takes off, starts running as fast as he can. What do? I sit down, and I take off my hunting boots, and I put on my really good Nike sneakers. And Greg says, Winn, what are you doing? What do you got to outrun the bear? And I go, no, Greg, I have to outrun you. Network security is a bear. Your homework is to do some of this. Try some of these things. Play with them. Tell us where we're right, where we're wrong, what the results that you're seeing are. We may be wrong in some areas. We would love to get some of these ideas and feedback. Again, feedback, in this case, positive feedback, to be able to help us make this whole process better. The axioms are there, always have been. If you want to go through the provable security model, you can blame Dr. Carney for establishing mathematically provable secure environments using the min-max feedback premises. My book is downstairs for sale. All of these are free on Amazon. And thank you very much. And I've got 51 seconds left. Thank you.